In this biomedical instrumentation lecture, we'll talk about measuring flow. Flow is defined as the volume of a liquid or gas moving per unit time and has typical units of milliliter per minute in clinical measurements. For a cylinder with a cross-sectional area of A, flow is equal to the average velocity of the fluid moving through it times that cross-sectional area A. So again here, this is the average velocity of fluid across that cross-section. And there are two different types of flow that you encounter in the body. One is laminar, where you have different velocities spread across the vessel, but there's no mixing, and the flow is all parallel. In turbulent flow, for example, what you would get if you had a kink in a tube, you're going to have jets that are going to go in different directions, sort of chaotically. When do we want to measure flow in the clinic? So the biggest one is blood flow. Ideally, what we really want is the oxygen that's delivered to the tissues, but we settle for blood flow as a surrogate measurement. We also measure flow to quantify respiration as an assessment of pulmonary function. And in various devices, we're interested in measuring flow. A very common one, for example, being a saline drip. So in this lecture, we'll talk about several different techniques for measuring flow. The first of which is just an illustrative example, which is a bucket and a stopwatch. Second is Doppler, an electromagnetic flow probe, a turbine cup anemometer, a hot wire anemometer, a differential pressure flow meter, and then in the next lecture we'll talk about indicator dilution, or fixed technique, which is specifically a method for measuring blood flow. For cardiac function. Okay, so the first one is just a bucket and stopwatch. So here we have some fluid flowing out of a pipe, going this way, and that fluid is flowing into a bucket that has these gradations on it such that we can see what the volume contained in the bucket is at any given point in time. And then we measure how fast the level of fluid in the bucket is reaching each gradation using a stopwatch. And what we do is we record that time difference or time lapse between gradations on the bucket. And that way we measure the volume per unit time. We can use the Doppler shift to measure fluid or particulate flow. Doppler can measure blood flow by bouncing sound waves off of moving red blood cells. So the Doppler shift then, as we talked about in a previous lecture, is equal to 2 times F naught times V times cos theta, where theta is the angle between the motion of the blood and the direction and the line connecting the Doppler device to that direction, and delta F is then the frequency shift that you receive. So C here in soft tissues is about 1500 meters per second, and velocity of blood is on the order of about 1 meter per second. So the illustration here is that we have, just to simplify it, we'll assume we have two transducers, one transmit and one receive. Here's the direction of blood flow. We'll have this reference axis here with which we measure the angle theta between the moving red blood cell, we'll draw it as sort of a kidney bean shape, and the transmit transducer. It will come, the pressure wave created by the transmitting transducer will hit the red blood cell, bounce off back to the receiving transducer. We're assuming that these two angles are the same. And then we can use a frequency to voltage conversion circuit to get a voltage output that is proportional to the frequency. So note here that the Doppler shift frequency is going to be on the order of 2, since we have a round trip, times 10 to the 6th, since our ultrasound frequency will be on the order of megahertz, times about 1.5, is about the speed of blood, 1.5 meters per second of blood in the fastest vessels, divided by the speed of sound is 1500 meters per second, which gives us frequency shifts on the order of 2 times 10 to the 3rd, or about 2 kilohertz. This is interesting because this is in the audible frequency range. So it's easy to make a device that transduces flow to a change in pitch of a sound. And also laser, in addition to ultrasound, laser is also often used to make Doppler measurements. Okay, so some constraints. One is that what we get here is the average flow, so you really have to know the diameter. Sorry, what we get here is the average velocity of the red blood cells. And so you really have to know the diameter of the vessel in order to infer flow. Laminar flow is assumed here. We're assuming that red blood cells are just traveling along a straight line. And it requires particulate flow. That is, it contains, so we can measure the flow of red blood cells in the serum, but we can't measure plasma without large particulates that will reflect off sound. There are some sources of error here inherent, as I said, since you have to know the cross-sectional area of the vessel to get the flow. If A changes, if that cross-sectional area changes, then you have errors in your measurement, and the speed of sound can also be erroneous. So now let's do a practice problem. Let's calculate the frequency of a Doppler ultrasound flow meter's output signal, where the flow meter has a carrier frequency of 7 megahertz. The transducer is sitting at an angle of 45 degrees with respect to the flow. The blood velocity is 150 centimeters per second, and the sound velocity is 1500 meters per second. So the previous equation tells us that the frequency shift is going to be equal to 2 times the fundamental frequency times V over C times cos theta. So this will be equal to 2 times 7 times 10 to the 6th times 1.5 divided by 1500 times cos of 45 degrees. that simplifies down to 2 times 7 times 10 to the third divided by root 2, which is approximately 10 kilohertz. So this is, again, in the audio range. The next device is an electromagnetic flow probe, and this is a really interesting and unique device for this application. So it turns out that these are the standard method for measuring flow in intact vessels. They are invasive because you have to wrap them around the vessel, but they are extremely accurate and easy to use. So how do they work? You have a magnet with two poles. Here's one pole of the magnet, and here's another pole, and that creates this B field going between the poles, right? This magnetic field that's static going between the poles. It's not changing in time. You also have the fluid flow, which is moving. The fluid is moving at a velocity v through the vessel, and what happens is that the B field interacts with the moving charges, which separates them across the vessel, and that gives you a measurable voltage difference across the sides of the vessel that is perpendicular to the direction to both the direction of the magnetic field and the direction of the fluid flow. So again, the magnetic field interacts with the moving charges, and this is determined by the Lorentz force, and that separates them across the vessel. That is, the force that they're experiencing is equal to their charge, Q, times the velocity, which is a vector quantity, cross product with the magnetic field B. That separation of charges creates an electrostatic force, which is given by the charge times the electric field, which is equal to the charge times the voltage divided by the vessel diameter. The forces balance, that is, F sub m equals F sub e, which means that Q times the velocity times the magnetic field, this here is assuming that the velocity is perpendicular to the field, is equal to Q times the voltage divided by the diameter, which means that V equals, the voltage that we measure is equal to the magnetic field B times the diameter L times the velocity V. So the velocity here is little v, and the voltage that we measure is capital V. So note that with this method, we're going to get the average flow. Like many other methods, we get the average flow in the vessel. So some strengths of the EM flow probe. One is that you can make continuous measurements, and it's one of the few methods that can continuously measure pulsatile flow. Pulsatile flow. Others measure actually time average flow. It does require charged particles, but it's independent of their concentration, or of conductivity, which is equal to the concentration of ions in the flowing fluid. The EM flow probes are very sensitive, and the physics are very well understood. They do have some weaknesses, though, in that principally that they are invasive and that they do require charged particles. Nevertheless, they're very widely used in physiology and also in industry. The turbine cup anemometer is a very simple device where you have a tube with fluid flowing through it. You have the velocity there, V, and then you literally just put a fan inside it, like a turbine inside it, that's attached to a shaft. It spins around the shaft. So the principle here is that the fluid or gas pushes on the rotor spins, and then the rate of rotation is going to be proportional to the velocity, which is proportional to the flow. Of course, these devices are not used in vivo because you have to stick them into a vessel. Weaknesses are that they have a delay to start up or spin down, so they don't have a super fast time response, and they are also invasive to flow, as I said. The fifth category is hot wire anemometer. The basic idea here is to heat up a wire or a resistor that is placed inside a vessel. The wire then loses heat to the flowing fluid or gas, and then its resistance changes. So here's another depiction. So you have the flow here through the vessel. You have a, let's say that we have a resistor crossing the cross section of the vessel. We have then an ammeter and a voltage source. Here that we use to measure the current. So this here is an ammeter, or a current meter, and then we have a fixed voltage here. This is one way to do it. And then the faster the flow, of course, the more heat is lost, and so then the resistance changes more. Often we use tungsten for these measurements in these devices. This rate of heat transfer is also a function of the specific heat of the fluid, which is equal to the amount of energy that's required to raise the temperature. It's ideal for measuring exhaled air, or inhaled or exhaled air, which does not contain particulates. So that's good because you don't want to have particulates. If you have it sitting in a fluid flow, for example, you can have particulate buildup that can hurt the performance of the device over time. There are multiple operating modes for these devices. You can run them. What I illustrated before was setting a constant voltage across the resistor and then measuring current. But conversely, you could have a constant current source and then measure the voltage across the resistance. Or you can try to maintain constant temperature and then measure both the voltage and the current. This would be a more sophisticated setup, but the advantage would be that it would be more resilient to burnout. So in this case, you'd have to have some kind of feedback to adjust the voltage or current source to maintain a constant temperature. Some strength of the hot wire anemometer is that it turns out it can measure rapid changes in flow. They're very small and simple, and they don't require any inertia to start, for example, a motor running or rotor turning. They have several weaknesses, though. One is that, again, they are invasive. They are nonlinear, since generally changes in resistance are nonlinear with temperature. Flow direction is unknowable, because since you're losing heat, but you don't know which direction the flow is going. And then they have a limited range, right, over which they are approximately linear. And the last kind of flow meter that we'll talk about in this lecture are differential pressure flow meters. So these are devices that are used to measure respiration, and they're called, a mainstay of the respiratory lab. So there are two different ways that we'll talk about to do it. One way to do it is to take a tube and put a mesh screen halfway in the middle, right in the middle of it, to create resistance to airflow, which creates a pressure drop on one side if air is flowing. So this would look like the following. You'd have two ports on this tube. You'd have flow could be going either direction. You put this mesh screen here to create resistance to the flow, and that's going to give you a pressure difference that you can measure on the between the two ports that are on either side of the screen. So then P1 minus P2 is going to be proportional to the flow. And again, this is the mesh screen that provides the resistance. Another way to do this is using the Venturi effect. So what we do here is infer flow from the difference in pressure between two pipes of different diameters. So here's the setup. You have two pipes that are connected to each other that have different cross-sectional areas, or diameters or cross-sectional areas. So the cross-sectional area of the bigger one we'll say is A1, and the smaller one we'll say is A2. And that means we're going to get different pressures if we have a constant flow through them. So we'll get P1 and P2. And it turns out that flow, Q, is equal to A1 times A2, the product of the cross-sectional areas, times the square root of 2 times P1 minus P2 divided by rho, the air density, times the difference of the squared cross-sectional areas. So again, this is the air density, which is typically 1.2 kilograms per meter cubed. And using either of these devices, we can make respiration measurements in order to assess lung function or diagnose asthma and pulmonary fibrosis. So here's what these tend to look like. So we'll plot here the air volume in the lung and define some parameters that are relevant for these measurements. So here on the y-axis we have the air volume in the lung, and then we have the total lung capacity on average. The total lung capacity is about 6 liters in males, or about 4.7 liters in females. Then, as somebody is breathing, normal tidal volume breathing, they're going to have some small change. If they take a big inhalation, they're going to hit the total lung capacity. If they do a big exhalation, they can never quite get all the air out, and then there's tidal breathing after that, what I'm illustrating there. So this distance between here and 0 is the residual volume, which is the smallest deflated volume. The tidal volume is the peak-to-peak volume of normal breathing, and that's on the order of 500 milliliters. This is a large inhalation. And the biggest change, that is the distance between the maximum volume and the residual volume, is called the vital capacity. It's the biggest change. Okay? So the procedure here to give vital capacity, which is a common measurement, is to have the subject simply forcibly exhale a full inspiration, right? Since that will cause them to go from here all the way down to here, and thus from that you can infer where the vital capacity is. And so let's finish this lecture off by discussing the strengths and weaknesses of the differential pressure flow meter. Its strengths are that it's very linear and it's simple. It's also very portable. You can make one with an Arduino pretty easily. And you can measure bidirectional flow. Since the direction that the flow is going will change the sign of the difference between the pressures. It's also very fast, and you can make continuous measurements. The weakness, of course, is that these are invasive to the flow. So you try to minimize the resistance that the subject is going to experience in blowing through them.